Module 3, Investigation 5, Inverse Functions, Reversing the Process. Number 1. For each of the following, describe what process would undo the given function process. So a function f multiplies its input values x by 5. That is, f of x is 5 times x. For example, if you multiplied an input of 7 by 5, your output would be 35. Like so. Number 1, what process undoes the process of multiplying each input value by 5? So let's think about what we just did with 7. We inputted 7 into our function, we multiplied it by 5, and we got 35. How could we undo that process to get back to where we started, to 7? We simply divide by 5. So dividing by 5 undoes the process of multiplying by 5. And this idea of undoing is at the core of the idea of an inverse function. The inverse function is what would take our output and send it back to the input. So in this example here, we could write f inverse of, let's see, 35 equals 7, because we would take our output and go back to the input. More on that later. Part 2, define a function h that undoes the process of f. So my function h is going to undo the process of f. So what it's going to have to do is, instead of multiplying by 5, it's going to divide by 5. And that's actually what we would call f inverse, and we could label it with this notation. F, that negative 1, just f inverse of x equals x over 5. Notice if we took 35 into this function, we'd have 35 over 5, which would give us 7. If you input 35 into the function h, the inverse process of f that you defined in 2, what is the output? Oh, this is what I just mentioned. H of 35 is 35 over 5, which is 7. So the output of h is what we got when we input into f. So since h undoes f, h is the inverse of f. Part B, a function g adds 17 to each input value x. That is, g of x equals x plus 17. For example, if you input 3 to g, you have g of 3 equals 3 plus 17 equals 20. What process undoes the process of adding 7 to every input value? Well, if we just added 17, if we just added 17 to an input value, to undo that we would simply subtract 17. Just do the opposite. Part 2, define a function j that undoes the process of adding 17 to every input value. Well, our j of x would simply be x minus 17. If you input 20 into the function j, the inverse process of g that you defined in 2, what is the output? Let's evaluate 20 in the function j. J of 20 equals 20 minus 17, which is 3. So notice what we have here. When we put 3 into the function g, which adds 17, we get 20. But when we put 20 into the function j, which subtracts 17, we get 3. So the function j undoes what the function g did. Part C says if you input a value into a function f, and then input the corresponding output value into the function that defines the inverse process of f, what do you notice? Well, anytime you input something into, we don't even have an f, that's supposed to be a g. Well, I guess you could say it's f. So just arbitrary function f. If we input a value into some random function f, and then take what we got, our output value, and we put it into the function that defines the inverse process of f, we just get back where we started. We saw that with g and j here. When we take something into g and we get our output, then if we plug that output into j, we get back where we started. We get the input. So we get back to where we started. The output of our function f, when made the input of the inverse process, results in the original input. The inverse process undoes the process of the original function. Part D. What conjecture do you make about h of f of x, where the functions h and f are defined in part A, assuming that the input and output to both functions is all real numbers? Part A. Okay, there's f of x and h of x. So what happens if we input something into f, and then we take that and input it for h? Well, we're just going to get back to x, because these functions are undoing each other. So composing a function f with its inverse h will return the original input value of x. Let's look more precisely about what we mean by that. Okay, so we had f of x was 5x, and then h of x was x over 5, and then notice if we take the composition h of f of x, that means that we take f and we substitute it in for h. So essentially we're going to put the 5x right here where the x is. H of 5x is 5x over 5, which is simply x. Notice how we take our input x and then we just return to the original input. Composing a function f with its inverse h will return the original input value of x. A new notation has been introduced by mathematicians to name a function that defines the inverse process of f. This notation, right here, f inverse, refers to the function that performs the inverse process of f on its input. Just like we said earlier, that f inverse for f of x equals 5x is x over 5. Even though the examples in exercise 1 are very simple, the idea of a function f and its inverse function f inverse as undoing each other applies in all contexts in which a function f has an inverse function f inverse. We will explore later in this investigation situations when a function f does not have an inverse function. However, if both f and inverse are functions that are defined for all real numbers, guaranteeing that the domain of f inverse is equal to the range of f, and the domain of f is equal to the range of f inverse, then anytime we take a composition of f and f inverse, whether it's f of f inverse of x or f inverse of f of x, we always get x. With our standard function composition notation, f of f inverse of x equals x and f inverse of f of x equals x, just notice that when you have a function composition involving inverses, they undo each other. So the input is your total resulting output. Number 2. When traveling outside of the United States, it is often useful to be able to convert between temperatures measured using the Fahrenheit scale and temperatures measured using the Celsius scale. The standard formula for determining temperatures in degrees Fahrenheit when given the temperature in degrees Celsius is F equals 9/5 C plus 32. We can write this formula using function notation by letting f equal g of c and g of c equal 9/5 c plus 32. Notice we simply replace the f with our function g of c. The function g defines a process for converting degrees Celsius to degrees Fahrenheit. Part A. State the meaning of g of 100 and evaluate g of 100. Notice that 100 degrees Celsius is our input. And so g of 100 tells us the temperature in Fahrenheit when the temperature in degrees Celsius is 100 degrees. Next we need to evaluate g of 100, which simply means plug 100 into our function, substitute 100 into this function. So g of 100 is equal to 9/5 times 100 plus 32, which is 212 degrees Fahrenheit, which you may recognize as the boiling temperature. I think that 212 degrees Fahrenheit is the boiling temperature for Fahrenheit, and 100 degrees Celsius is boiling for Celsius. Next, part B says, solve the equation g of c equals 212 and explain how you arrived at your answer. Well, we know that g of 100 equals 212 from part A, so we know that c equals 100 is our solution. We know that when the temperature is 212 degrees Fahrenheit, the temperature in Celsius will be 100 degrees. Now, if you didn't know this, how would we solve the problem? Well, you know that g of c equals 212, so you'd replace this g of c here with 212, and then you'd simply solve your formula or your equation for c. You can subtract 32 from both sides, and we'll get 180 equals 9/5 c. And then you could either divide by 9/5 or you could multiply by the reciprocal. 9/5 times 180. That will give you c. Notice that actually that's not the reciprocal. Sorry about that. Reciprocal of 9/5 is 5/9, so multiply 5/9 times 9/5 to get 1, you get c by itself, and 5/9 times 80 is 100. Part C, define a function h that converts Fahrenheit temperature to its Celsius temperature. Hint, generalize the steps you described in part B that reversed the process of g. You can also solve f equals 9/5 c plus 32 for c. So we want a function h that converts Fahrenheit temperature to its Celsius temperature. So we want our input to be Fahrenheit and get Celsius as the output. And so we have here the Fahrenheit is determined by the temperature in degrees Celsius. So just like we did above here, 212 minus 32, we just take our temperature in Fahrenheit, subtract 32, and then we multiply that result by 5/9 to give us c, which we want our function to be called h. So h of f equals 5/9 f minus 32. Part D says determine the values of g of 100 and h of 212. This is pretty simple. We just substitute 100 in for g and 212 in for h. So I've worked that process out for you here. Just made a small mistake. This is actually 100 and you don't need this. Okay, make sure you can do that process on your own. Part E, determine the values of g of h of 212 and h of g of 100 without performing any calculations. What do you notice about the relationship between g and h? Well, let's see. H of 212, we know that that is 100, and then if we make that the input for g, we get 212. And then g of 100 is 212, and if we plug that into h, we get 100. So, clearly, g of h of 212 is simply 212, and h of g of 100 is simply 100. And so what do you notice about the relationship between g and h? Well, g and h are inverse processes because they undo each other, or inverse functions. Part F. Represent the value of g of h of n. Represent the value of h of g of k. What do you notice about the relation? Represent the value of h of g of k. What do you notice about the relationship between g and h? Okay, so g of h of n let's remind ourselves, what are g and h? G of c is 9/5 c plus 32. H of f is 5/9 f minus 32. So g of h of n, first we plug into the h function like so. Then we substitute this into the g function. 9/5 all of this plus 32. So let's simplify this a little bit. Right here we can multiply 9/5 times 5/9, and that's just 1. So we have 1 times n minus 32, which is n minus 32, plus 32, which is simply n, which is what we expect when we compose one function with its inverse. And that's this, what do you notice about the relationship question? We notice that the input here is also the output. That signifies g and h are inverses, as long as the reverse holds. H of g of k, well, g of k, if we look back up here, g of c is 9/5 c plus 32. So g of k is 9/5 k plus 32. And we want to substitute this expression in as the input for h. And notice h of f is 5/9 f minus 32. So h of 9/5 k plus 32 is 5/9 9/5 k plus 32 and minus 32. So again, I just took g of k and put it in place here for f. Notice 32 minus 32 is 0, so we have 5/9 equals 9/5 k, and then 5/9 times 9/5 is 1, so we just get k. So what do you notice? We notice that the input here, k, is the same as the output, so g and h are inverse functions because they each undo one another. Two functions are said to be inverses of each other if any input value of the composed function results in an output value that is the same as the original input value. So two functions u and v are inverses of each other when u of v of n equals n and v of u of m equals m for any values of n and m that make sense in the context of functions u and v. The functions for converting from degrees Celsius to degrees Fahrenheit and from degrees Fahrenheit to degrees Celsius are inverses of each other. Another way to think of functions that are inverses of each other is that each function undoes what the other function does to its input. A function that is the inverse of a function f is represented as f inverse. Note, f inverse does not mean 1 over f. Be careful not to confuse the inverse of a function f, a function that undoes the process of f, with the idea of inverting a number. Recall that the inverse of a number such as 2 is written 2 inverse equals 1/2. And the inverse of a variable x is written x inverse equals 1 over x. And why do we use that notation? Well, they undo each other. Notice that 2 times the inverse of 2 is 2 times 1/2. Just 1. 1 is our identity function. I'm sorry, it's really the identity element. And here, 1 or x times x inverse equals 1. there's an analog with functions. We always get the identity function when we compose a function with its inverse. The identity function means that the input is always mapped back to itself. So that's a abstract mathematics concept. If you like math, take abstract algebra and learn more about that. Number 3, use functions h and g defined above in exercise number 2. Okay, let's remember what those were. So here's g and h. It is correct to say that the function h undoes the process defined by the function g. But why? Notice that if we look at g, it takes the Celsius temperature, multiplies by 9/5, then it adds 32. Then h undoes that process. It subtracts 32, and then it multiplies by the reciprocal of 5/9, which is the same as dividing by 9/5. So it undoes what g did. And same thing here. The function h takes f, subtracts 32, and multiplies by 5/9. Well, to undo that, we'd multiply by 9/5, then add 32. So yes, all the operations of h are the opposite functions of g. Adding 32, subtracting 32, multiplying by 9/5, multiplying by 5/9, each of those would undo the previous operation. How would you represent the fact that h is the inverse function of g? Well, I would probably just say h is equal to g inverse, but the book has this weird diagram that I'll draw for you guys. So here's the diagram. Notice if the input is temperature measured in degrees Celsius, the function g tells us the output is the temperature measured in degrees Fahrenheit. Then if we input the temperature in degrees Fahrenheit, then into function h, then the output is the temperature in degrees Celsius. And so basically g takes some input here, but h takes us right back to where we started, to that same temperature. Same thing with h. If we input some temperature f, then g is going to take us right back where we started. So they undo each other. Number 4, use the given table to evaluate the following. So we have our table, we have our inputs x here, and we have the output of f of x and the output of g of x. First thing that we want is g inverse of 3. So we just have to undo what g has done. So if the output of g was 3, we would undo that by going back to 1, or negative 1, sorry, right here. Notice that g of x, when x is negative 1, g of negative 1 equals 3. Now remember, the inverse undoes what has been done. So g inverse essentially says if you get an output of 3, then the input must have been negative 1. You may remember from high school somebody said the domain and range are swapped for inverse functions. Essentially, the output of the original function is the input of the inverse function. So g inverse of 0, well, look here where the output of g is 0, then the inverse will take us right back where we started, to 3. F of g of 0, this is a review. G of 0 is 2, and then f of 2 is 6. F inverse of negative 1, here's negative 1, and we will just want to go back to find the original input. X is 1. Now, g inverse of f inverse of 6. Well, first of all, f inverse of 6, we look at 6 here as our output, then the input would have been 2. Then g inverse of 2 would be 0. Lastly, f inverse of g of 2. Well, g of 2 is our input. The output is -1 from g. Then we want the inverse of f. So here, that means the output was -1, and the original input would be x or 1. Number 5, given the function f defined by f of x equals x squared, we have f of 2 equals 4. So just looking at the graph here, here's the input is 2, the output is 4, so f of 2 equals 4. F of -2 equals 4, that's represented right here on the graph. Input is -2, output is 4. And we know each output value of f greater than 0 is paired with 2 input values. Notice, like for here, the output value of 4, there's 2 values that go with it. -2 and 2 are the 2 input values that go with that. If we picked an output value of, say, 8, there's an input value here, looks like 2.7, and an output here about -2.7. I'm sorry, those are both inputs that correspond to the output 8. So we want to evaluate f inverse of 4. So meaning we want to undo what f did. So f of x gives us 4, but how do we undo it? Do we undo it and go back to 2, or do we undo it and go back to -2? This is not defined because there are 2 outputs, or 2 inputs for the same output. When I say not defined, it means we don't know definitely where to go. Do we go back to -2 or 2? We don't know how to undo the function f. The book says that f inverse of 4 has 2 output values, -2 and 2. Remember, the inverse is just a function, but their input and outputs are reversed. So f inverse of 4, here 4 is kind of like the input, but we're going backwards, and then there's 2 output values, -2 and 2. Recall that the definition of a function says that each input from a function's domain is paired with exactly 1 output value in the function's range. Since inputting 4 to f inverse returns output values of 2 and -2, we conclude that f inverse is not a function. Number 6. Given f of r equals 4 pi r squared is the function whose input is the radius of a sphere in inches and whose output is the surface area of the sphere in square inches. Evaluate f inverse of 115. Explain the meaning of your answer. So let's think about this for a second. The f inverse would undo what's already been done. So that means that 115 had to be the output of f. That's going to be the surface area of the sphere in square inches, 115 square inches. Then if we evaluate f inverse of 115, we'll find the radius of the sphere that gives us a surface area of 115 square inches. So the question is, how do we do this? Well, to evaluate f of inverse of 115 means to determine what input to the function f will result in an output of 115. So that tells us that our output is 115. We have our function f of r equals 4 pi r squared. That f of r is the output, and so we need our output to be 115, and we'll get a resulting equation that we can solve for the radius. Notice that to solve for the radius, we divide both sides here by 4 pi. And that gives us 115 over 4 pi equals r squared. And then to solve for r, if r squared is 115 over 4 pi, then the square root of 115 over 4 pi will give us r. Notice we don't need a plus or minus here because our radius can't be negative. And so we get 3.025. And so to explain the meaning of our answer, just like we said here, 3.025 is the radius that will result in an area of the sphere being 115 square inches. Part B, determine the inverse function f inverse that undoes the process of f. Describe the process, input quantity and output quantity of f inverse. So let's talk about this in a couple different ways. First, notice what f does to the radius. It squares it, then it multiplies by 4 pi. So if we want an inverse function, it'll have to divide by 4 pi, then take the square root. It will do the opposite. And we've actually got our formula for the inverse right here. Pretty much. So again, note that f squares the radius and multiplies by 4 pi. So we square the radius, multiply by 4 pi to obtain the area. So to undo this process, we need to divide the area by 4 pi as we did here. We divided 115 by 4 pi and then take the square root. So our f inverse, which is a function of the area, can simply be calculated by taking our area, dividing by 4 pi, and then taking the square root of the result. Notice that this gives us a radius, so we could say that our total output of the inverse function is a radius value. Some of you may remember a different process from high school. Anytime you wanted to find an inverse function, like you could change f to y, something like this. Then you could swap x and y. And then you could solve for y. I'm sure you guys saw something like that probably. Take the square root. And so we have pretty much the same thing here. It's the square root of a over 4 pi. I think the last step in this memorized process was to swap x and y again or something weird like that. maybe not. So yeah, here we got our inverse function. So explain what it means to evaluate f inverse of 26.7. Notice that this simply means that we're taking a surface area A here and we're calculating the radius of the sphere that would result in the surface area being 26.7 inches squared. Part D, explain what it means to solve f of x equals 26.7 for x. So here, f of x, that was the original function here. So x would be a radius, and the output gives you the area. So this 26.7 is an area, and we'd be looking for the radius that gives us the value of 26.7 for the area. Notice that it's exactly the same as in part C. So why does this make sense? So this makes sense because the output quantity of the function f is the same as the input quantity of the function f inverse. They just undo each other. The domain and range are swapped, inputs and outputs are reversed. Think about that. I think this is number 7. It may say number 6 in your book. The function f defined below gives the volume of a sphere as a function of its radius length. 4 pi r cubed. What is the domain of f? Well, think about what f is for a second. It's the volume of a sphere with a certain radius. The domain is the set of all possible inputs, and so it doesn't make sense to think of negative radii, but we could think of any numbers in between 0 going up to as big as we wanted our radius to be. So we could say that the domain is all the numbers from 0 to positive infinity. Notice I didn't include 0 because I'm guessing that if the radius is 0 you won't even have a sphere, so you can't even talk about its volume. So I think these are all the possible inputs, any positive number basically. So what is the range of f? Notice that the volume of the sphere will increase if the radius increases. So we just have to find the minimum value of our range, which we get just by plugging 0 into the function. And then the volume is just going to increase as long as the radius increases, the volume will increase too. And notice that f of 0 is simply 0. So any value in between 0 and infinity, those are the possible volumes. That's our range. Possible outputs. Determine a formula for the inverse of the function f. What is the input quantity of f inverse? What is the output quantity of f inverse? Okay, let's think about f inverse for a second. Notice that the input of f is a radius and the output is the volume. So for f inverse, what is the input quantity? It's going to be reversed. It's going to be the volume. And what is the output quantity? That's going to be the radius. So our inverse is going to take as its input a volume. Now notice we just have to undo what happened above here. So we take our radius, we cube it, and we multiply by 4/3 pi. So essentially, all we have to do here is when we get our volume, we would divide by 4/3 pi, undoing the multiplication. And then we could take the cube root, would undo the cube. Now anytime you divide by a fraction, you can flip it and multiply. Dividing by a fraction is the same as multiplying by the reciprocal. This is really 3/4 v times, or v over pi. Either answer is okay. Let's see, and that's again the cube root out here. I think probably some of you guys want a more like sound mathematical way to do this than just thinking about what happens to the output. So let's go back to your high school method again. Notice f of r is 4/3 pi r cubed. That 4/3 pi r cubed, that outputs a volume. Let's swap those. R equals 4/3 pi r cubed, because if we want the inverse function, we need to swap the inputs and the outputs. And let's just solve this equation. To solve, we could multiply by 3/4 r and then we could divide by pi. Let me just take this a step further here. We could divide by pi, and that'll just put the pi down here in our denominator. We'll have v cubed, and we can take the cube root of both sides to get the cube root of 3/4 r over pi equals the volume. And then, this is why that method is really weird, you just have to swap them back. So it has to be the cube root of 3v over 4 pi equals r. Probably a better way to do this would just be to not swap those. That's kind of a weird thing. Yeah, I don't know if that's a good idea. Or you could just think of undoing the function. Part D, what is the domain of f inverse? What is the range of f inverse? So take a look at here, our f inverse. Remember that we have volumes is now the input of f inverse, and all our possible volumes are from 0 to infinity. And then the range is all the possible radii, which are from 0 to infinity as well. Okay, I think this is problem 8. Might say 7 in your book. Determine a formula that undoes the process of each of the given formulas. So I'll try to give you guys a couple different ways to solve these. This is a equals f of s equals s squared. So just think, what would undo a square? It would be a square root. Notice the input of the original function was s, and so the output was an a value, so the input of the inverse function will be a and the output will be an s. So one other way you could have done this one, just say a equals s squared, take the square root of both sides, ta-da! Okay, d equals f of t equals 56t. So we're multiplying t by 56. So to undo this, we would just divide by 56. But notice that the input is t, the output is d, so it'll really be d divided by 56 is f inverse of d. So how else could we have done that? Let's just say d equals 56t. Just solve for the input, since the input just reverses those. D over t equals, d over 56 equals t. And so we can say that that's our f inverse of d. And in this one we could have said that our f inverse of a is square root of a. Alright, y equals f of x minus 8. So to undo that, we would just take y and add 8 to it. So here's how you could do it systematically. Just say y equals x minus 8. Add 8 to both sides. Y plus 8 equals x. That means your inverse is y plus 8. Okay, part D. A equals pi r squared. Let me do it this way first. A equals pi r squared. Divide by pi. Take the square root, and that gives us r, which we could call f inverse. Another way you could look at it is if you take r as your input, you square it, and you multiply by pi. So that means if you want to get r as the output, you just undo everything that you did to your area. Instead of multiplying by pi, we divide by pi. Then instead of squaring, we take a square root. Alright, part E. Last one. Y equals 2x minus 5 over 6. Notice that our inverse function will give us x. The outputs and inverse are swapped. And since we take x, we multiply by 2, then we add 5, and then divide by 6, we just reverse that process and undo it. So instead of the last thing we did, which was divide by 6, we're going to take the y value and multiply by 6. And then instead of subtracting 5, we're going to add a 5. Then instead of multiplying by 2, we're going to divide by 2. Take a look at how this process would work here. If we solve for x, we multiply both sides by 6. That would cancel this 6 here. We add 5 to both sides. Divide by 2. And then we wind up with the same thing.